Think forward. Think Research Channel.
Actually, you'll notice if you're an astute audience that I've modified my title from the original advertise of Sociopaths to Autocrats upon advice of counsel. So what I want to do this evening is in about an hour take you through kind of a discussion, a very actually quick discussion to explain what I said in 8 seconds this morning on the soundbite on the Today Show. And hopefully I can explain a little bit more than I was able to do then. As I get started, I want to make sure that I acknowledge the people who have helped fund a lot of the research that I'm going to be basing my observations on this evening. National Science Foundation, NASA, Federal Aviation Administration are primary funders of the research at our center here. But I also want to make it quite clear, and I have made it clear to them, that the comments I'm making tonight are my own and do not represent those of our graduate students or of our sponsors. This is just a list of some of the people who are working in our laboratory. We'll see if this pointer works. It's pretty light. And so we have a number of PhD students who are working in this lab and a number of our faculty. So it's a lot of the comments that I'm going to make or the data that I'm going to be discussing is really the work of many other people, not just myself. I think a fundamental question that I like to ask, and I never want to pass up an opportunity to collect data, is, why do people fly? It's a mode of transportation. Typically, people want to fly because they want to get someplace fast. It's usually a long distance, so speed is important. Safety is important always. That's one of the main things the federal government tries to do is regulate the safety of the system. Personally, I like a predictable schedule. I love traveling in Switzerland and Germany where the trains run on time. I like to know where I'm going to get there. Affordability, of course, is important, and reasonable comfort. So I'd like to ask and to collect a little bit of data from my audience. Audience participation is kind of good to see if you're listening. First of all, how many of you in the audience have experienced a flight delay in excess of 15 minutes? Okay, I think I got that. Anything less than 15 minutes, the FAA doesn't count as a delay. Okay, so how many of you now have had your flight canceled by the FAA because of weather? So maybe 50% or so. That's an interesting number. We'll come back to that. Security line longer than 15 minutes? That's pretty higher than 50%. And how many of you decided to mode switch? Drive to some place or take the train that you used to fly to? Maybe 20, 25%. Okay. There's a lot of things that this complex adaptive system is doing, and I want to talk about and try to explain why these are all actually very important things, and I appreciate collecting that data. What I'm telling you right now is in the realm of background. One of the things that one of our current PhD students is doing is trying to develop a new metric for passenger delay as opposed to flight delay, because actually passengers were the things that are moving through the system. The FAA doesn't report passenger delay, and they don't, in fact, try to manage the system to care about your delay. But if you can extract out of the databases, which we are doing, you can come up with a number of statistics, and one of them I find interesting is this probability of your flight being delayed for more than an hour. And I pick an hour because that's kind of a hub turn time that you might have in your schedule, and you might miss a hub connection if your delay is more than an hour. So in the probability, these are kind of the worst airports. In 2004 and 2005, we're just now starting to process the 2006 data. And what you'll notice is that for 2004 Chicago, if you were hubbing through Chicago, you had a 12% chance of having your flight delay be longer than an hour. And this might go up to 24 hours. I mean, this is just greater than an hour. Newark was the second worst, LaGuardia third, Philadelphia. These are all really bad actors. My advice to you, by the way, is if you can avoid these airports, do so. I do. I try to avoid them. 2005, some things happened. Chicago, actually, the FAA administrator kind of came in and strong-armed and forced the airlines to change their schedule. Now, this 1978, the airlines were deregulated, so this is kind of a slow movement back to kind of backroom regulation. But Chicago got better. So Newark and LaGuardia moved up to the top pole positions. Notice that they were getting worse. And I think as we look at the 2006 data, we're going to find that they're even worse than 2005. And I'm asking my student actually to do 2002 through 2006 just to look at a longer-term trend line. But the problem is this is going to get worse. And I think in my discussions with a number of people in this town is that there's a growing sense that this is inevitable. We just have to put up with it. It's kind of like death and taxes. This is not inevitable. The system doesn't have to operate this way. There are lots of places in the rest of the world that don't operate this way. Well, before you just start blaming the airlines as being nasty people and they're doing all this to us, let me point out the airlines are not in all that great a shape either. And this curve is from the Air Transport Association, so I've gone back and looked at all the data from 1960 on. 1960 was kind of the beginning of jet travel. That's when air transportation really took off in this country and in the world. And so this kind of maroon, whatever color this is, a line, is in constant dollars. So this has been adjusted for inflation to $2004. This is profit, this is loss. This is for the entire U.S. air transportation industry. Okay. And what you'll see, it's gone up and down, and this is if you integrate this, or if you just kind of add all this together, profits and losses, this is the cumulative profit since 1960 of the entire U.S. air transportation industry. And what you should notice is that right now, it is a negative $2.8 billion. They have lost $2.8 billion more than they have ever earned since 1960. This is not good for them, and it's not good for us either. I'm not going to, this is a busy slide, and I know it's too small to read. I just want to point out that Chapter 11 is called bankruptcy. Chapter 7 is actually liquidation. These are just a number of airlines since 1982 that have gone into bankruptcy, mostly in and out. Some of them finally go completely out into liquidation. We have 3 right now, ATA, Delta, and Northwestern are currently still in bankruptcy. It's not a healthy industry. What is important to understand is that there is no air traffic control system modernization that you might read about in the newspaper or hear about in television that is going to fix any of these problems. This is a complex adaptive system. It is a public and private partnership. Federal government does some things, the private sector does things. And we have, in operations research, we talk about objective functions, things you try to optimize, and we have very conflicting objective functions between the public and the private sector. The public sector is interested in commerce, it's interested in public safety. Because it's public, it has politics, and because it has politics, it has lobbies. So those are very important parts of the dynamic of the public sector decisions. The private sector is pretty simple. It's called profit maximization. If you can't make money, there's no reason to stay in business. If the airlines all went out of business, we would have no air transportation system. There is no movement afoot, and I think no political pressure to take over the air transportation industry. And so one way you can kind of look at this, and this way I'm currently looking at this, is a stack of 6 layers. Each one of these layers is a network unto itself, and they're all based on the bottom of this as on government regulatory control layer. It really is the foundation of how everything else works. There's then a physical layer, and we have cities. The cities have certain kinds of airports. There's demographics associated with those cities, which generates pressures for flows between the cities. It's a very important part of the dynamic of our system. We have a weather layer. There are things that airplanes don't like. I mean, actually, cars don't like them either. Ice storms, hurricanes, tornadoes, and so we have to adapt to that kind of semi-unpredictable things. We have a government layer, and I've added TSA to this recently, TSA and the FAA. FAA has air traffic control radars. They have VHF radios, control centers, unions. All these things are an important part of this government layer. TSA has almost the equivalent things now for security. On top of that is the airline layer. They have to make capital investments in their airplanes. They decide on what routes they're going to serve, what the schedules are, the aircraft size on that route. These are incredibly important aspects of how well the whole system works. And then finally, at the top of this, there's us, passengers and cargo that move in the system, and that's the whole reason that all the other layers exist, is kind of to move us around for commerce, etc. And I don't expect you, I'm not going to brief the slide to show you that the interactions between those layers is extremely complex. There are many loops. These are feedback loops. They're nonlinear. And a lot of our research is oriented on trying to understand the nature of these loops. What are these relationships? How do they work? And what is the effect? When you push on something over here, how does it wind up over here with our flight delays? And that is one of the things I think has been missing in government policy, is not taking into account the full complexity of the interactions that are involved here. So this is all kind of background and motivation for this talk. My view is, and why we're doing research here, is that this is bad. It's bad for the U.S. economy. Air transportation is a vital artery of economic growth. It's bad for us, you and me, because we actually like to travel. Probably I do. I would say now, this is where, of course, none of our sponsors now will take any accountability for what I'm saying at this point, but Congress is both the problem and the solution. There is no satellite-based system. This was Marion Blakey this morning on the Today Show with the same bit that I was on, said, well, we need a whole new system, automation, satellites, and those aren't bad things. Those aren't going to solve the problem. And by the way, those aren't even promised until 2025. So this is setting up, okay, my talk. I'm going to try to say, who are the prisoners? There are prisoners in this tale. Who are the sheep, and who are the autocrats? So background. For those of you who don't know, this is kind of a picture of the nation's network. These are jetways. These are air traffic control sector boundaries. It's very complicated, more complicated than an interstate highway system because you have altitude, you have time synchronization. The FAA operates as basically, my analogy of the private sector is a wireless telecommunication company with inputs from some surveillance sensors. There's a lot of stuff that goes on here. All of them have the kind of the same technical characteristics of Singular and AT&T. There's a center here that I think is important that you should understand because we're going to talk about later, and this is an Air Operations Center, Central Flow Control here in Herndon, Virginia, and they do something called ground delay programs. Which has probably affected most of the people here who've had delays, but you didn't realize it was being affected here in some decisions that are being made between the FAA and airlines. So I'll come back to that. This is a map of the U.S. Each one of these dots, I don't know how it looks out there, but is an airplane. It's a loft. Typically from 8:30 in the morning to 8:30 at night, there's about 6,000 airplanes that are in the air under positive control from the FAA. 2 million passengers a day are moving through this system. These areas are the areas that are of special concern to us. There's a triangle from Minneapolis, St. Paul to Boston to Atlanta. This is equivalent to the core of Europe. It's a very high density area, very complex, and the source of a lot of our problems for the whole nation's air traffic control system. You obviously have this West Coast area from San Diego to San Francisco. You have some big activity here in Dallas, Fort Worth, and Houston. And Denver is kind of sitting out here in the middle doing some interesting hub operations. If you go into that triangle, the northeast, this is Pennsylvania, New York, Washington, D.C. This is a snapshot of aircraft aloft in the northeast, and it's busy up here. But controller workload, one of the things that one of our doctoral students did, and he finished his PhD in 2005, is we use very elaborate computer models where we actually model controller workload. And it's a very complex function of aircraft. They're going up and down, and they're talking to each other. And this is a map in colors, so it's a kind of a pseudo map where red is high workload and blue is low workload. And this is a snapshot at one time in the day, so it moves around somewhat as the day goes on. But what you'll see is there are these hot spots, but the point I would like to make is a lot of dark blue. There's a lot of this system that is not high workload. And so in general, the en route part of the air traffic control system is not the problem. That's not what's causing congestion. It used to be called, it's the big sky. You put the airplane out, you launch the airplane, it goes in the big sky, you bring it down someplace else, that's all you have to worry about. Big sky for en route is still probably not a bad metaphor. So, it's the airports. We're going to talk a lot about the airports. They're the problem. Why are they the problem? Well, this is a network, and so an airport is a node in the network. And the thing that's really important that sets the capacity of the system is safety separation time. Now, any of you, if you've recently gotten a driver's license someplace or taken a driving test, and the Federal Highway Administration says 4 seconds or 5 seconds is what you should leave between you and the car in front of you. That's what gives you adequate braking time in case they decide to stop. It's really not a distance. It used to be a distance. They've now gone to time separation. That's the important parameter. It's true for aircraft as well. So for us, and that's what drives the capacity, we're going to talk about 2 times that are important. One is runway occupancy time. How long is an airplane on the runway? And the inter-arrival time. How close are 2 airplanes in the landing process behind each other? And I'm going to tell you without a lot of proof that 90 seconds is a pretty good number for airplanes, as opposed to the 4 seconds for car. You're landing an airplane that's 100, 200, 300, 400, 500,000 pounds, going 150 miles an hour. It's got to stop within 2 miles, and it's got an airplane right in front of it. So the FAA and the whole world kind of has a rule that says we don't want to have 2 airplanes on the same runway at the same time. That kind of gives us some separation, so something happens to that airplane in front, blows a tire, brakes get locked up, can't get off the active runway. You don't have an airplane that's coming in behind it that cannot stop before it hits the airplane in front of it. It's a pretty conservative rule. It's not a bad rule. If you follow that rule, that would say 40 arrivals per runway per hour. That's a capacity for a good runway. So you kind of keep that in mind, 40. But these are not synchronized. These schedules aren't synchronized. We have competition. We'll talk more about that. So it's an asynchronous arrival stream, and there's a theory that goes with that called queuing theory. And what you'll see, and I'll show you an example, at about 80% of that maximum safety number, or 32 arrivals per runway per hour, is kind of the onset of serious delays. So if you schedule beyond 80%, you're going to just, math tells you, and the experiment, the data bears it out, you're going to start losing predictability. So this is kind of queuing theory. So if this is a non-dimensional number, it's the demand, how many airplanes want to land, how many are scheduled to land over the maximum capacity, maybe 40 arrivals per runway per hour. So, if those are exactly equal, that would be 1. And what queuing theory says is that the delays are infinitely large. Now, in practice, the theory starts breaking down there. It doesn't go to infinity, but the data is pretty good. This is the theoretical curve. And what you'll see is at 80% capacity, which is roughly 32 arrivals per runway per hour, you get about 15 minutes delay. And the FAA says that's okay. I think that's probably okay. There are lots of things in the system you can't really control. But you go just a little bit above that, and the delays start going up non-linearly. And somewhere up here around 90%, you start seeing airlines canceling flights. They cancel flights. These are congestion cancellations, not because the airplane's not working. It's because they're losing schedule integrity. The delay is just too long. That airplane's got to be someplace else. They've got to move the airplanes around on their daily schedule. So delays and cancellations are correlated. Most people think only about delays. You have to also worry about cancellations. So let me show you some data. This is how we collect it, and we have 2 doctoral dissertations that have been completed here in this area, but very simple schematic. You have an airplane landing. This is the runway. Once it crosses this threshold, we start the clock. We stop the clock when it gets off the runway. That's called runway occupancy time. There's a plane coming in behind the first one. The first one crosses this threshold. We start the clock. The second one crosses this threshold. We stop the clock. That's the inter-arrival time. So you can measure these. This is just a scatter plot. Okay, I won't go into all the statistical calculations we do, but this is kind of instructive. This is this inter-arrival time in seconds. So right here is 90 seconds. That's the 40 arrivals per runway per hour, which is kind of a safety limit. Turns out that the runway occupancy time, the average occupancy time for an airplane, it's kind of a design point, is between 45 and 50 seconds, with about an 8-second standard deviation. So this standard deviation is just spread. So what we have here is the length of time that the airplane stayed on the runway versus the length of time that the airplane coming in behind it is. And what we don't want is simultaneous runway occupancies. And these 3 points right here are a time when the airplane in front stayed on the runway a little long. The airline coming in behind it, the airplane coming in behind it was pretty close. And both airplanes were on the same runway at the same time. That should happen on the order of once or twice a year if you really followed the safety regs. This happened 3 times in 1 week at a major airport. Okay, well, that's the way the system actually works so capacity and safety are linked. My point here is they're not unrelated. The reason that we have the delays is because we're trying to enforce some separation between airplanes to maintain safety buffers. And there's a lot of spread here. Okay, efficiently, if we really wanted to get rid of delays or get the most out of the system, we'd like to get all these long times between airplanes pushed over closer to 90 seconds. And we'd like to not have all these times that are a little bit shorter than we would like them to be for safety reasons. And this can be done today's airplanes for at least 10 years, maybe 15 years, have had the technology to do required time of arrival. And I believe slot controls, which would regulate how airplanes actually are synchronized coming into airports, can greatly increase the efficiency. Over here, new avionics that have been developed and new procedures that have been talked about but not implemented could greatly reduce this scatter, this variability, so that we could gain both capacity and safety in modernization. It requires changes in FAA procedures. It requires the adoption of slot controls, which we're almost unique in the world for industrialized nations of having very few slot-controlled airports. Mandating of new avionics, which have been developed but not mandated, to kind of make the system have more capacity with safety. So this is our summary. You want to think about this, 40 is kind of the maximum for capacity, 32 if you want predictability, and the FAA needs to step up to the bar to actually make these things happen. But delays are not limited to single airports, and this is something that's coming very strongly out of our research, that this is a network problem. And I want to go through some examples to show you how delays propagate between different airports. And part of it is the fact that the schedules are not coordinated at any given airport, and that's driven by antitrust laws. Okay, American can't sit down with United and say, okay, I'm going to take the first 5 landings in this 15-minute interval, you take the next 5. That would be an antitrust violation. And I think the antitrust laws are good. The airlines have suggested maybe they should be suspended for them to work on this problem. I don't think that would be the right answer, but it is a problem. We have almost no slot allocations in this country. A few airports have it. LaGuardia has it, Washington National, Kennedy, Chicago, but those are kind of drifting away in the laws. But the schedules are key. Schedules are really key to solving this problem, and so it becomes difficult. FAA can't control schedules. Scheduling decisions are driven by airline concerns, and they're reasonable concerns. They want market access. Everybody wants to go to LaGuardia. Competition. Everybody wants to go to LaGuardia. And profitability. They want to make money. That's why they usually want to get into these markets. But delay then, and what we see very clearly in our data and in our models, delay at a few major airports impact the entire air transportation network. So I'm going to go to the first question is, who are the prisoners? Well, let's look at airlines. These are the latest Bureau of Transportation statistics on comparing the performance of the major airlines. I'm leaving out the Hawaiian Airlines, so that's why we start at 3. They have really no problems because they fly mostly out of our system. This is percent on-time performance. That's what DOT reports. So the best airlines are Frontier and Southwest, up here at 87%, 84% on time. That means they don't trigger the 15-minute number. But then what you see is the vast majority are all around here, 75 to 77% of their flights on time. That means roughly 25% of their flights are not on time. These are yearly averages. Okay. Then other things, you can pull these together. Well, how about involuntary bumping? This is the rate per 10,000 operations. All the people in yellow are worse than the mean. So I'm just kind of pointing out who the bad actors are here. And then percent canceled. You don't get that in one table, so I've pulled these things together. So even though United Airlines, as shown here, is doing pretty good, 79% on time, turns out that 1.2% of their flights are canceled, which is almost it's twice what Frontier is doing. Some of these airlines are, 3% of all their flights. Comair is really a turkey. So just, and it's just what the data says. So there is some variability from the best to the worst, but most of them here are, quite frankly, pretty much the same. There's not a lot in quality of service to differentiate the airlines. That's a network effect. If you look across airports, I'm just going to say here are some primary ones. Most of these are bad actor airports. Atlanta Hartsfield, bad airport. Chicago O'Hare, bad. Philadelphia, all three New York airports, and Dulles in Washington is getting to be a bad actor. These are airports that generate delays for the entire network, largely because they're overscheduled, okay? And there's no real regulation to not prevent them from doing that. And so if you look across, these are all the airlines that fly through these networks. What you'll see is that, for example, United Airlines, who's got an average across these airports of 72% on time, or conversely, 28% not on time, some of them a lot not on time, not much different, including Denver. Denver is one of the newest, it is the newest airport in the United States, clean sheet of paper, over $5 billion, came online about 1995, 6 independent runways, probably the largest technical capacity airport in the world. And its delays are almost as bad as the worst airports in the United States. Why is that? We tend to say, well, we'll fix this airport. Chicago will put a new runway on, and that's going to solve the problem. Atlanta just put a 5th runway on. Did that solve a problem? Our data is indicating not really. And that's an important thing that we're trying to work on. Just to give you some advice, these are time of day. The best the system ever works is from 6 to 8 a.m. in the morning. So that's a good time for you to fly, okay? It's about 90% on time at most of these airports. The worst time in the world to fly a scheduled flight, either arrival or departure, is 7 to 8 p.m. at night. And you can get airports like LaGuardia, the average on-time performance is 50%. The average, okay? At Newark, it's 39% on arrival, 47% on departures. My view is you're crazy if you hub through Newark. If you expect to get someplace. I refuse to do it. Okay, so how do you regulate this thing with airports? I just say, I pointed out something that the FAA, after 1978, there's deregulation. Before the FAA doesn't control those slots. There are no slots at most of these airports, but at some of them there are. And it's called, there's a high density rule. It was at Newark, EWR is Newark, LaGuardia, JFK, these are the 3 New York airports, DCA, Washington National, Chicago O'Hare. And there are some perimeter rules that go there. 1969 was the first time we got into congestion at these airports. And the government limited the number of scheduled flights into those airports to control congestion and delays. That was a good thing. Almost all the industrialized world has slot controls on their major airports. In the early 1990s, Newark was taken out of these controls. I have no idea why. And it's been a terrible airport ever since. 1978 was deregulation. This is when the government says we shouldn't even be in this business. Very shortly after that, the introduction of the hub and spoke system, which is inherently efficient. But it also now puts real pressure on some key airports. And those airports affect the entire network. 1985, the people who still had slots had them ceded to them by the federal government, said you actually own these. Now they can also take it back, but right now the airlines think they own those time slots. And the authorization bill for 2001 took the slots off of LaGuardia that had been on there since 1968. LaGuardia turned into a parking lot. It was a disaster. So let me give you a little case study on LaGuardia Airport. That's one of my favorite airports for doing research on. I will not fly there, but it is a great airport to do research on. It's a very simple airport. It's an old airport. It's about the same vintage as Washington National. So it has kind of the old geometry. 2 runways at 90 degrees angles to each other. 1 typically for arrivals, 1 typically for departures. That's kind of their normal operational mode. This is a picture of it. One of the reasons why there's only 2 runways here and no more is they're kind of surrounded by water. There's kind of like no place to grow. They're already on landfill. So what happens at this airport? Well, there are roughly 93,000 flights a year. The average flight delay over the whole year and over all the entire day is 38 minutes per flight at LaGuardia. The average seat throughput, so if you just take all the planes with all the seats on them, is about 9 million. The actual number of passengers that go through there is about 7 million. That's a load factor. Load factor is on the airplane is kind of what's the fraction that's full. That's important for profitability. So at LaGuardia, the average load factor is 78%. Rule of thumb is you can do more than 70, you make money. If you have less than 70, you lose money. The average passenger airplane size is about a 96 passenger airplane, and the average intercity fare or the segment fare is $133. That's a fact. That was 2005. We modeled this airport and we looked at the primary 67 daily markets. So daily scheduled flights, 67, these are just kind of where LaGuardia, these people fly, high density rule, but you get some flights to Denver, some to Houston. That's kind of the longest you get to fly. Big flights here, red is the number of flights per day, is to Washington, D.C., Boston, and to Chicago, the shuttle flights. Those really drive that schedule at LaGuardia. Not surprising. Okay, this may be hard to see for the people in the back, but I'm going to bear with me. This is data on the scheduled flights at the 3 New York airports. So this is Kennedy, this is Newark, and this is LaGuardia. And this is 1. This is a ratio again. So it's the ratio of scheduled flights divided by what the FAA says is the maximum acceptable safety operational rate. Roughly the 40 runway arrivals per hour. Remember, 1 runway for landing, 1 for taking off, easy to analyze. And what you'll see is that all 3 of these airports, this is by time, by the way, this is January of 2000, probably the worst, that's what I said on the Day Show, that's the worst in history for the performance of the U.S., and by the way, that's the worst in the world, to January of 2006. Okay, so here, these airports were, this is 80%, so this is the 32 arrivals per runway per hour, kind of predictability area. Anything below this gives you kind of predictable travel. Anything above this is questionable on the safety of the system. Well, they were running all 3 about 90%. So they're kind of in that nonlinear area where you just expect a lot of delays. On this chart down here, this is delays in minutes, average delays in minutes. So this line is 1 hour delay per flight on average. And you'll see that all 3 of the New York airports in January of 2000 were running an average of about 40 to 45 minutes delay per flight when they're scheduled at about 90% of maximum capacity. Well, then the congressional authorization law, Air 21, came into place. It says we're going to take those lot controls off of LaGuardia. And we're going to let a whole bunch of new entrants in. Well, immediately the airline scheduled 20% more flights, 20% more than what the FAA said is the maximum safe capacity of that airport. That's nothing illegal about that. So they scheduled up here. This is what happened to the delays at LaGuardia. Delays went up to an average delay of between 85, almost 90 seconds per flight in LaGuardia delay. Now it turns out that of this 20% increase, probably no more than 10% ever even flew that generated this delay. The rest were canceled. They did this for a number of months. They sold you tickets on flights that they knew they were going to cancel. Okay. Well, LaGuardia complained that their airport was no longer a functioning transportation node and had been turned into a parking lot. So they asked for some relief. So a lot of political things happened, and they decided to cut back the number of these increased slots and allocate some new ones by lottery, sometimes called the slottery. So they forced this schedule down to only 10% above maximum safe capacity. Interesting number. The delays came down, but what happened, of course, about the same time as 9/11 happened. And so kind of the bottom dropped out of the demand for air travel. People were afraid of it, et cetera. This is kind of what happened. And so, it got to be pretty good. 2002 was a good year for air transportation compared to 2000 because the demand went away. Well, I guess the good and bad news is that the demand is back. Okay, so all the airports have recovered. So Kennedy and Newark are operating back again here above 80%. Their delays are up. And LaGuardia is back over 100% of maximum capacity, and their delays are up. And what you'll notice, though, is an interesting factor. All three of these airports, this is their delay, go up and down seasonally. They're very closely coupled, because it's not just the airports themselves, it's the airspace around them. And so a delay at JFK or turning a runway around affects the other airports. They all affect each other. These are network problems. You cannot solve these things with fixing an individual airport. But we're running the system at saturation. You might think, but they're making money. Okay, so it's, even though the delays are bad, the predictability is not terribly good, but at least we're moving people through and the airlines are making some money on it. So this is a chart that one of our doctoral students, Luann Lee, who just finished her PhD, pulled out. And this is 6 months of data in 2005. These are for all those 67 city pairs, and each dot represents an airplane size. So this is like an airplane with 200 seats in it. This would be an airplane with 100 seats in it. These are the load factors. How full are those airplanes? So these big red lines here indicate anything that's above this had a load factor of above 65%. That's 50% of all the flights. 50% of all the data points are above this line, so they had above 65%. 50% of all the data points are above this line at about 110 seats. Okay. So these are big airplanes. These are big, full airplanes. This is a real good area. We call this the win-win area. LaGuardia, Port Authority, New York, New Jersey would like to have lots of people going through their airport so they can do commerce. Chamber of Commerce likes that, and these are full airplanes, so the airlines like it. They're making money in all these flights. This is 25% of all the flights are in kind of this win-win category. The interesting quadrant is down here. 25% of all of the flights are in a lose-lose quadrant. These airlines are small. The airplanes are small. Most of them are regional jets at 50 or 30 seats. They have almost no passengers in them, certainly under the break-even point. And this 25% of the flights are the 25% that puts LaGuardia over the top into both the unsafe area, or where safety is a concern, and also into the extremely high delay area. They're not bringing many passengers into New York, and they're not generating any profit for the airlines. So you have to ask the question of, why would they do that? Okay. Why do the airlines schedule beyond the safe maximum capacity with flights that lose revenue? And that's, I think, an interesting aspect of our research that we're struggling with trying to understand that. And there are several reasons. First of all, there's no government regulation that prevents them from doing this. Okay? And this was actually kind of what I think in hindsight's always 20/20, it was probably an error in the Deregulation Act of 1978. And from the airline standpoint, they've told me this frequently, personally. They do surveys. Their vice president of marketing goes out and does a survey and says, what will you want? They said, well, we like frequency of service. We'd like to be able to fly to LaGuardia anytime we want to, every hour, every half hour, every 15 minutes if you'll give it to us. And we like cheap flights. This is kind of a no-brainer. So the marketing department tells the scheduler, schedule up, every 15 minutes a flight between Boston and LaGuardia. Marketeer guy doesn't say, what's the safe capacity? He says, is there any legal restriction? Schedule guy says, no, there's no legal restriction, so schedule it. Okay, the passengers, however, in these surveys are never told of the consequences. They're not said, would you like frequency of service or would you like predictability? You can't have both. So it's kind of like an error in how the data is collected. And as the airlines explained, if any one airline decided to be a good actor at LaGuardia, they really don't trust the other guys. The other guys are going to schedule up. They're going to take market away from them. They're going to lose even more money. If the FAA ever decides to throttle back, they're going to probably do it from how many flights you've got scheduled. And so when Air 21 hit, all of the airlines who are going into LaGuardia pumped their schedules up unbelievably, knowing that it was going to absolutely kill their performance, and knowing that they couldn't actually fly all those flights physically. And by the way, anybody who'd be a good actor would just let the other people still do the same thing, and they're going to get the same delays whether they're a good actor or not. So in game theory, this is called the prisoner's dilemma. Okay, and lots have been done on this, but so this gets to the answer to my very first question. Who are the prisoners in this story? And it really is the airlines. They're giving us terrible, terrible service because the devil is making them do it. and they're actually kind of right. Okay. What they told me one day in a technical meeting we were at, where I had a very blunt discussion with them, I said, "Why are you doing this?" They said, "Look, we're playing by the rules. If you don't like our behavior, change the rules." And they were exactly right. So there's a question, if we had more rules, let's say we had an aggressive slot control program where we restricted these airports to only 80% of maximum capacity, and we capped them, what would happen? And this is a question the Department of Transportation asked us in some research we're doing here. Their concern was, if we interfere with the market by trying to use safety and predictability as a constraint on these airports, what's going to happen to the transportation network? What are these airlines, because that's the private sector, is going to operate independently of what the government does, what markets will be served? What's going to happen to the schedules, the frequency, the equipment? How would passenger demand change at the airports, the routes? How would airfares change? All these are very legitimate questions, and so we tried to address those, and one of our doctoral students did a mathematical model of this entire system. We looked only at LaGuardia because it was a well-posed problem. In this case, we looked at auctioning slots to let the market decide who should have access to these vital resources. I'm going to show you only one case at 32, kind of the predictable level. What if we restricted LaGuardia to a predictability constraint, and we take all of the databases that the government has, we include the price elasticity for all those 67 routes. This is real data. We do a network flow optimization problem. We actually solve the scheduling problem so people can get in and get out. We run a delay network simulation to see what's the consequences of doing this on delay, and we get things out which are flight schedules, fleet mix, average fare, flight delays, profit, etc. And what we found is that by government regulation, to regulate to predictability and safety, to restrict the schedules back, we can find win-win solutions. It's counterintuitive. By restricting and regulating, we actually help everybody. Turns out the airlines were able to achieve within 90% of optimum profitability, which is better than they're doing today. Almost all the markets were retained. They reduced frequency because they just put some larger airplanes on. So those RJs kind of all mostly went away, a few stayed. But you got a lot of 737s that were booked in there. At less frequency, they actually carried more passengers. The airports won because they reduced the delays by 70%. This is a very nonlinear function. Just that reduction of 8 arrivals per hour from where we're trying to run today at over 40 reduced the delays there by 70%. The passengers got better improved predictability. The airfares didn't change, and almost all the markets were served. Air traffic control reduced the probability of simultaneous runway occupancy and became much more scheduled for them. So this was actually a win-win. So, and that helps the prisoners because it puts a government regulation on them and they know how to work within that regulation. Let's now go to say, who are the sheep? Well, all of us have had flights canceled. All of us have had flights delay. I've been told frequently, the FAA canceled your flight. That is not true. The FAA does not cancel anybody's flights. If there's a weather event, the FAA does things like ground delay programs. They will reduce the arrival rate to what is called an instrument meteorological capacity rate. But they will tell the airlines, we're reducing the arrival rate now, what do you want to do about it? The airlines make the decisions in a conference call that starts about 6 hours in the morning before the first flights go and lasts all day long, called collaborative decision making, in a barter and negotiation where the FAA is kind of a broker. And the airlines are trading off which flights are actually going to run, which ones are going to cancel. Airlines cancel flights. Airlines decide which flights are going to be delayed. Here's an example. This is real data. July 7th, 2004, there was a strong line of thunderstorms moving across the East Coast, kind of a typical thing we would see in the spring, for example, or summer. The weather, the FAA said we're going to have a ground delay program, GDP, at 10 airports. So these red dots were the airports that were now put into a ground delay program. So the airlines now say, okay, they're reducing the arrival and departure rates at those airports because of this weather event, so they made decisions on what they're going to do with their flights. In this particular case, 87,000 flight minutes of ground delay were imposed on the aircraft running through the system. I will point out the FAA knows very little about weather or route structures. Route structure is an airline decision that's Actually, they probably shouldn't know much about it, but they don't. And I will say that they're not too keen on weather. This is kind of what happened. Okay, this was that flight restriction area. These are all the flights that were affected by that ground delay program that never were flying through that zone in the first place. So 80% of the flights affected by this GDP, okay, 2,289, did not go through the FCA. Over 69,000 minutes of those delays were unnecessary. If you ask the FAA, and I've seen some of my FAA colleagues, former colleagues in the audience, they would say that's not their job. And in some sense, they're probably right. But the overall system is not working properly. There's some little known facts. Okay, I'm both, my PhD is in aeronautical engineering. I look at this picture and I say, well, this was a DC-6 here in 1947. IOC, first operational capability. Propeller-driven, subsonic airplane. This is a state-of-the-art 737-900 Boeing airplane. Gate-to-gate time between these two airplanes for much of the Northeast is longer today or the same time as it was in 1947. Schedule padding, one of the main. However, this airplane is 70% faster and can fly 80% higher, this airplane over that airplane. This airplane can fly over most bad weather. It's one of the main differences in the development of this type of airplane with the jet engines. And this airplane has got called a Category 3 landing. It can land in 0-0 visibility, hands off, very elaborate, very sophisticated computer controls in the airplane. So airport congestion causes most of these delays, not weather. In fact, if you look at GDPs, and we're doing statistics on this right now, many of the GDPs happen every day, no matter what the weather is, and there are usually restrictions because of overscheduling at key airports. But weather can oftentimes be, what are you going to say about the weather? You can't control that. So passenger quality of service. These are, the FAA and the industry is focused on flight delays. But the real important thing here is passenger delay. And in the cost-benefit analysis the government goes through for doing any modernization, they primarily look at fuel burn, fuel consumption for the airlines, not lost passenger human productivity time. What we're seeing in our analysis is that the amount of lost passenger time is almost as bad and maybe of equal value as the fuel burn losses to the airlines. And to get this, you have to really look at cancellations, not just delays. So we're developing a new quality of service metric. Danny Wang, who's one of our students who is in the program right now, is doing this work. Looking at the major 35 airport networks, sometimes called the OEP network, 2004 data. This 35 airport network in the United States accounted for 3 million flights to over 1,000 city pairs. 20% of all of those flights in 2005 were delayed for more than 15 minutes. As you look into the details of that, that's 52 million hours of passenger delay. 1.8% of those flights were canceled. When you look into the details of that, and it takes a lot of analysis to be able to get this out, to our surprise, about 34 million hours of delay from flight cancellations. So 1/10 of the flights were canceled, but almost the same amount of passenger delay. It's because those cancellations lead to really big delays. At $30 an hour, which is kind of an average of what the government says your time is worth, about $2.6 billion per year in lost human productivity, and there is no federal requirement for the airlines to provide any compensation for that. So what are your rights as a passenger? Okay, airlines do not guarantee their schedules. What you're buying when you buy a ticket, and if you really press them, they'll say you basically bought a lottery ticket. And I showed you some of the statistics earlier and what your chances were of getting your flight through. There's no federal requirement for delays or cancellations. Airlines are free to bargain with each passenger they strand. That's kind of in the official DOT language. If you go to their website and say, they said, do the best, negotiate, get whatever you can get. Overbooking is legal. The rights for involuntary bumping due to overbooking is if you have a 1 to 2 hour delay, $200 maximum, not even up to your ticket price. If it's greater than 2 hours, which could be 24 hours or 48 hours, $400 maximum. Europe, however, has adopted a passenger's bill of rights, which gives you a lot of rights. And I don't have the time to go into it today. You can go to websites and find it. My advice to you, if you're flying internationally, fly a European airline and hub through a European airport. You pick up rights, and you're going to get a lot more predictability. Okay, moving into, we're still in the sheep segment here. This is not the only problem. TSA and security after 9/11 has become a big problem. So I'm going to talk a little bit about some of the work that I'm doing on terrorism. I used to do a lot of work in the military and defense. And I know something about terrorists. And the reason terrorists do what they do is not to take and hold territory. This is not the kind of war that you would think of, World War II. They do things to get headlines. They're trying to affect political changes. And they do this by getting in the press. And so they need to have something that's big. A 9/11 was a big thing, killed 3,000 people, okay? Knives and guns are simply not the problem for security and air transportation. I mean, it used to be when somebody says, well, I want to hijack this plane to go to Cuba, and we'd take them. But locking those cockpit doors is an extremely good and cost-effective thing to do. And so if you're in the back and you pull out a gun or a knife, you might kill 1 or 2 or 3 people. Well, that's a bad time. Last weekend we had 4 people killed in 5 hours. That just happens. I grew up in Houston. That was a bad night in Houston almost every night. So that's not the security problem. It's killing a lot of people to make a political statement. We are actually trying to guarantee 100% safety with a static security line. And I'm going to, this is like I call the French Maginot Line defense philosophy. It's a classic example. Explosives are our problem, and nitroglycerin, as one example, very easy to make. Learned how to make it in high school chemistry lab, 30, 40 years, whatever it was I was in high school. Had some of my classmates almost blow themselves to bits doing that, but it's straightforward. In fact, there are a lot of explosives that you can make. And I will show you that the large security lines created by this Maginot Line of security create what I'll call killing zones, mass soft targets. And they do that before there's any security screening whatsoever. These long security queues not only are generating unsafe situations, but increasing the lack of predictability in transportation. The passengers here, I really believe, are being treated like sheep. Let me say something about the Maginot Line. The French spent 10 years and great national wealth after World War I building this static line so that Germany could never invade France again. Many, many billions of francs, 10 years of work, and in 5 days, Germany went around it in 1940. It was a false sense of security. Those in the military analysis business, and General Karl von Clausewitz, for those of you who are military historians, said it very succinctly in 1830 in his writings on war. If you entrench yourself behind strong fortifications, you compel the enemy to seek a solution elsewhere. Case study, Washington Dulles. This is a computer model that we have of Washington Dulles. This is the curb up here at the top. Okay, these are the ticket counters. These are the security check-in queues. We can model different passenger loads going all the way through this in simulations. It's kind of what we do in system engineering operations research. Blow up with the details of the magnetometer, X-ray machines, how people go through this, what the delay times are, etc. When you do that and you look at what happens at 8 o'clock in the morning or 4 o'clock in the afternoon, I've been there myself many times. These are these little Disneyland kind of queues that they build up. This shows every one of these little circles is a person. This is a soft target killing zone if I were in the defense business. And I would like to put an explosive in here, 10 pounds of HE with nails, screws, ball bearings, would kill 2 to 3 plane loads of people, and that's before there's any explosive security screening. This happens at least 10 to 15 airports across the country at the same time. A coordinated attack would be the equivalent of 9/11 in lives lost. We're paying an awful lot of money for this security system. The airlines are paying out of their profit margin over $2 billion per year to supply this security system. I will say, based upon what I showed you earlier, the airlines are in fact not financially capable. They're net in the hole $2.8 billion. $2 billion a year of lost revenue to them is a lot of money of lost revenue. We need the airlines to survive to give us an air transportation system. They're basically, in my view, making a donation to a national publicity fund. This is more of a statement of public will. However, these airlines have systemic deep operating deficits. They have low profit margins. They've defaulted or are defaulting on their pension plans. And I would say if the government decides that they really want to do this as a statement, then they ought to use the general revenue funds and not the airline ticket tax. So the answer to my second question, who are the sheep in the system? You are the sheep in the system. It's the way you're treated by everybody. Okay, what has really changed technically? I want to kind of finish up here with my last question. Go back to my airlines. Okay, I'm an aero engineer. This is a subsonic airplane because I can look at the airfoils. It's also subsonic because of the speed and the altitude. I can look at the compressors on these jet engines versus these propellers. So it goes higher, 40,000 feet for this airplane versus maybe roughly 20,000 for that. I told you it goes faster. There's now radar separation. 1947, we didn't do that. But the big difference here is on the flight deck. Okay, this is the 737 flight deck. This is the DC 7 flight deck. We now have computer flight management systems, something called required navigation performance, 0.1 nautical miles, okay, with 98% probability. You know where you are at all the time and can control that. We can have required time of arrival to within 30 seconds. We have onboard traffic collision avoidance systems. We have Air Operations Center data links, like your digital data phone. We have zero visibility landing systems. What has not changed is that we still talk to air traffic control on World War II AM push-to-talk radios. That's a problem. The FAA has two separate functions, for those of you who are not familiar with this agency. First of all, I will say they're a regulatory agents. They regulate the airlines, make sure that they maintain their airplanes properly, they operate them safely. They regulate the aircraft manufacturers, make sure they design them properly and safely. And then there's an air traffic management operator, the safety oversight of itself. Okay? Many industrialized nations, in fact, have gone away from that business model for many reasons. They weren't able to use federal employees to properly modernize, they didn't have access to investment capital, and they were concerned that they didn't have an independent safety oversight role of the government on top of the air traffic operations system. It's a legitimate concern. I am now leaving the realm of data and analysis, and I'm now, that's what the yellow up there, I'm now going into my opinion. Why is this happening? First of all, the FAA is an organization. I served with them for 5 years, 4 of them managing the modernization of the system. Their culture and the engineering expertise within the FAA is not up to running, managing, constantly upgrading technically a modern digital telecommunication system. Because they are a monopolist, they exhibit monopolist behavior. There is no accountability for them to not improve. They are not held accountable. And secondly, it is not in the self-interest of the union, NATCA. Some people think when I talk about this, they say, well, Reagan broke the union. That was called PATCO. That was in 1981. Yes, he did.